All right, welcome back. In this video, what we're going to do is we're going to explore the fundamental theorem of calculus. The fundamental theorem of calculus, what it will do is it will evaluate the value of the definite integral without graphing it, without using approximations, underestimates, overestimates. Two primary parts of the definite integral, or of the fundamental theorem of calculus. If you have a definite integral from a to b of f of x dx, you can take the antiderivative at the top limit minus the antiderivative at the bottom limit, and that will give you the area. If you have u substitution, we write it this way. We've got to write it this way so that what we do is we change those limits. I'll show you some examples of that in just a moment. If we have, on a definite integral, if you have an even function, and even functions are symmetrical over the y-axis, you can see this is the even function. If we have it from negative a up to positive a, we can double it from 0 to a. That's easier. So we just take that area is the same as that area, so we just double it. If we have an odd function from negative a to positive a, it's just 0 because this area is negative, this area is positive. Remember, odd functions are symmetrical around the origin, even functions are symmetrical around the y-axis. The second part of the fundamental theorem of calculus says that if you take the derivative of the integral from a constant value up to a variable expression, it's just going to be my integrand at that upper limit. If that upper limit is something other than just x, like if it's x squared, we've got to use a little bit of chain rule, and we've got to multiply by the derivative of that upper limit as well. I'll show you some examples of that later in the video as well. All right, here we go. First one, the definite integral from 0 to 2 of this polynomial function. So if we just take the antiderivative, which would be x to the fourth minus x cubed plus 2x squared minus x. We use a vertical line or integral notation, lower limit 0. Upper limit is 2. If I plugged in 2 there, I get 16 minus 8 plus 8 minus 2 minus, when I plug in the lower limit, it's just 0. And so when I work that out, I got 14. No, you don't have to use the u substitution, so you don't need to change the limits or any of that kind of stuff. When I do change the limits, when I do have to use u substitution, like in this one I have to use that, u is going to be 4 minus x. And then du is negative dx. I'm going to multiply by negative 1 when I rewrite this. So I put a negative out front of the integral. I rewrite the integral. I'm going to change my limits now. So if I change my limits by putting 0 in for x right here, which is going to be 4, and 3 in for x right there, that's going to be 1. I'm going to pull that 2 as a constant. I'm going to pull that guy out front. Anytime you pull constants out front, these would be great. This part right here is going to be u to the negative 1/2 power. One little small thing before I take the antiderivative, I may change these limits because they're switched and get rid of this negative, so I can rewrite it as 2 times the integral from 1 to 4 of u to the negative 1/2 du. When I take the antiderivative then, it's going to be u to the 1/2 divided by 1/2, which is multiplying by 2. So ultimately this problem becomes this. It becomes 4 times u to the 1/2 at 1 and at 4. And again, pull those constants out front, it really helps you. So it'd be 4 times, and if I put 4 in there, the square root of 4 is 2. Put 1 in there, it's 1. So my answer is just 4. Yes, you have to change the limits. I'll clarify this in class, but you do have to change the limits. My next example, the sine of 2x. So now I have to use u substitution again. So u is 2x, du is 2 dx. Multiply the integral by 1/2. So it's going to be a 1/2 out front. If I put 0 in there, I still have 0. Pi over 4 in there, I get pi over 2 of the sine of u du. Now, once you do u substitution and you change your limits, you no longer are going to put in 2x. 2x is gone. So the 1/2 stays out front. The antiderivative of the sine of u is going to be negative cosine of u at 0 and pi over 2. So negative 1/2. Cosine of pi over 2 is going to be 0 minus the cosine of 0 is 1. So this is going to become positive 1/2. We're to our second part of the fundamental theorem of calculus, where we're taking the derivative of the integral from a constant value up to a variable expression. In this particular case, I just have an x as my upper limit, so it's going to be the integrand at that upper limit. So my answer here is going to be the sine of x squared. And that's it. You don't have to do anything else. This integrand, you can't evaluate the antiderivative of that by hand. If I have something other than just x on this upper limit, like here I have x squared times e to the t dt, and I want to find the derivative of g at 2. So when I find the derivative, like if I were to find this, the derivative of the integral from 0 to x squared of e to the t dt. If I were to find that derivative, it's going to be e to the x squared, the integrand at that upper limit, but because that upper limit is something other than just x, I have to multiply by the derivative of that upper limit because of chain rule. So this is times 2x. And that is my derivative. And then I'm asking you to find the derivative at 2, so it would end up being 4 times e to the 4th. All right, good luck. I'll see you in class. Clarify as much as possibly can.